All right, folks, video number 2, we get to the good stuff, which are examples that you guys could do along with me here. So without further ado, go ahead and try it. Number 7 and 8 here, just in front of us. Ready, set, go. I can read it out loud for you. Suppose you want to prove that triangle RST is similar to triangle XYZ. By the SSS similarity theorem, state the extended proportion you'll need to prove first. Suppose you want to prove that triangle RST is similar to triangle XYZ by the SAS similarity theorem. If you know that angle R is congruent to angle X, what else would you need to prove? Okay, ready, set, go. Think about it, think about it, think about it. Learned these 2 similarity theorems in the video. Didn't you watch the proofs of it? You did. Give it 30 more seconds. Ready, set, go. Ready to go on with this one here? Okay. All right, so let's review this one real quick here. Again, I hope you watched the last video. We rolled out, we proved for it. Oh man, it's a great proof. The SASS similarity theorem, okay? So SSS similarity theorem is that if we knew if all sides in proportion, then triangles are similar, okay? Right, that's the SSS similarity theorem. Okay, here we got some triangles here, and what's not said in the theorem, but what's implied is that you need to be corresponding as well here too, okay? So that means that RS to XY, if we knew that that is in a particular ratio, because again, those sides are corresponding here. RS and XY we have here. ST and YZ also correspond, okay? If that's in the same ratio as, oops, let's just write ST here, ST to YZ, okay? And I also knew that, here I got to do the last 2. RT is the last 2. RT to XZ would be the third side here. And there you have it, okay? So there's your answer to number 7. That's the extended proportion. If you knew this, that RX to XY were maybe in a 3 to 4 ratio, ST to YZ is in a 6 to 8 ratio, RT to XZ is an 8 to 10 ratio, boom. You know that those 2, 8 to 12 ratio. You know that those 2 triangles would have to be similar to by reason of the SSS similarity theorem. Okay, I already proved it with you, right? Don't worry about the angles, the SSS similarity theorem. Okay, number 2 here, we got, suppose you want to prove that triangle RST is similar to triangle XYZ by the SAS similarity theorem. If you know that angle R, there we go, we got angle R and angle X are congruent, okay? They're corresponding, that's very nice, right? They're in corresponding positions. This is position 1, the way we read out. Remember, the ordering of the letters matters here, right? That's one thing I had to check in with some people on the chapter 4 quiz is that this would imply that R would have to be congruent to angle X because corresponding angles of similar triangles are congruent to one another, okay? But we want to prove this here. So we're given that angle R is congruent to angle X. What else would you need to prove? Well, we need to prove, if we're using SAS similarity theorem, okay, that one says that if 2 angles congruent and their sides including the angles are what? In proportion. What else would you need to prove? We need to prove that the sides including those angles are in proportion, right? Then triangles are similar. Okay, similar. So here, what's going to include angle R? Okay, well, I got R, so angle R goes off, and one of the sides that's part of angle R is RS. Okay, so I have RS over here, and I also have, what's the other side? Well, we have T, we have R here. There we go, that's what I'm looking for, RT, okay? So those 2 sides include angle R. Over here, XY, well, that goes to RS, okay? RS to XY. RT, I already filled out the answer up here, but it'd be XY, right? Oh, wait, no, they moved it around, didn't they? No, they the same way. What am I doing here? RT, XZ, oh, my bad, yeah, XZ. So here, RT, and then XZ also includes angle X, right? So we have that one here, and they're in corresponding positions, okay? So if I know, right, if I knew that angle R congruent to angle X, and I knew this, then I'd be able to use SAS similarity theorem to prove that that triangle is similar to that triangle. Neat, just neat stuff here. All right, we got another one for you guys that I usually do in class when we usually do this as a normal lesson, and I'm like, hey, go do your homework. So give this one a shot here. Can the 2 triangles shown be similar to one another? If so, state similarity reason. Hey guys, this might come up on your exit ticket. It just might. I don't know. I don't remember. I did those a long time ago. There's a lot to do. There's a lot to do. Ready, set, go. Give it a shot here. Can the two triangles shown be similar? If so, state the similarity reason. See if you can find it. Who sees it? Who sees it? Let's go. Give you 1 minute, and then we'll go over.
Do you wanna know that it doesn't hurt me?
15 seconds. 7 seconds. All right, let's do this. So the key words that were written in these directions here, it says, can you prove them? Can you prove them? Okay, is it possible here? And obviously, you know, when you have diagrams like this, boom, vertical angles, you can put them in here, okay? And it looks like here, yes, 9 to 12 is in a 3 to 4 ratio, 6 to 8 is in a 3 to 4 ratio. So, hey, our goal here of showing that BT to OT would have to equal OA to OK is true because it's a 3 to 4 ratio, 3 to 4 ratio. So that's true. And we also know that angle KOT congruent to angle AOB. Okay, so that's not angle O, but it's like the vertex here because vertical angles are congruent. So this one is yes. Okay, so state the similarity reason. This would be SAS similarity. Okay, I would include that similar too. Because why? Because we have an SAS congruency postulate now. So this is SAS similarity theorem. Okay, just don't say SAS. Say SAS similarity. I might write that back to you if you do that here. All right, check this one out here. We got 70 degrees. We got 40 degrees. We got 70 degrees. We got 60 degrees. So at surface level, well, no, this isn't AA. We don't know anything about the sides, so we don't have to worry about SAS or SSS similarity. So maybe let's write down what the unknown angle is here. Okay, what's this one? What does this one measure? Angle J. Well, that would be 180, right? Because the three angles added together equal 180. Then it's going to take away how many other angle measurements the other angles are. So I'm going to take away 70, take away 60, and I get what? 180 minus 70 is 110 minus 60 equals 50. And hey, check it out over here. Oh, wait. So yeah, no. The answer is no. Did I do that one wrong? Let's see here. 180 minus 70 is 110 minus 60 is 50. So yeah. Doesn't work out here, okay? If I wanted to double check that I did this one right, because this is a 50-degree angle. So here, this is a 40-degree angle, and there's no 40-degree angle in this triangle. So this one is no. And if I wanted to be 110% sure I got this one right, I'd just double check again here. 180 minus 70 is 110. Minus 40 is, what, 80 degrees? Okay, and yeah, these are not, right? No, not similar. They're not similar, okay? This one here, what are we doing? Mark up those vertical angles, okay? Does that help you? No, it doesn't, because check it out here. These vertical angles here, their included sides would be CA. So CA to CE is in that 1 to 2 ratio here. AB to DE is in that 1 to 2 ratio here. But check it out, AB doesn't include angle ACB. DE doesn't include angle DCE because you're either including that angle or you're opposite that angle. So DE is opposite this angle here. So CD and BC, those include angle BCA and angle DCE, but we don't know what ratio they're in, right? We don't know. So we don't know. We can't conclude here, okay? So we can't conclude. So no conclusion about similarity, okay? This one up top here, we knew they weren't similar because those angles weren't all congruent to one another here. Here we can make no conclusion about similarity. Let's check this one out here. Okay, so we got here FH. We know this, FH to, what's the smallest? So this is the smallest here. So smallest to smallest. This is how I would arrange this. Smallest to smallest, and then I go medium to medium to see this matches up here, okay? So FH to RX is 10 over 16. Okay, I might simplify that so we can figure out the common ratio. So these are both divisible by 2. So this is 5/8. Okay, and here we got HG to XS, and this is 15 over 30. So wait, no, hold on. That's the longest side. Sorry, I wanted the middle side. So this is RS. Okay, HG is the middle, so that's the middle length, right? It goes 10, 15, 20. This one goes 16, 24, 32. So this is 15 over 24. And these are both divisible by 3. So this is going to be 5, and then 8 divided by 3 is 24 divided by 3 is 8. So this is 5/8 too. So that checks out. Last side, is it going to be in a 5:8 ratio? So let's check this one out here. So I'll grab this 20 and 24. Oh, no. 20 and 32, largest to largest here. Those are both divisible by 4. And yeah, it's going to work out here because 32 divided by 4 is 8. And 20 divided by 4 is 5. Okay, so we have this. They all are in a 5:8 ratio. Okay, so this is going to be yes, and by the SSS similarity theorem. Okay, SSS similarity theorem. That's for number 4. Okay, number 5. Ooh, this got kind of cut off. This looks like 25 here. This one looks like 9 here. This is a little tricky. So a triangle shown similar. So first of all, there are 3 triangles in this diagram here. We got LPA, LPN, and LNA. There are 3 triangles. It's a bit hard to figure out what's going on in this one here. So you might have some trouble with this. So this is a little tricky. And maybe I need more space to actually show this here. So this is in a 15 to 25 ratio. This is in a 9 to 15 ratio. So let's check it out here. This one here, I think they're talking about these ones. Let's look at these ones here, because LN is not part of the larger triangle, so let's ignore that. So we're talking about this triangle here, and we're talking about this other triangle, the smallest one in the diagram here. That's how we're gonna have to think about it. And what's hard about this, and this is a very common diagram you're gonna be dealing with in the coming chapters here, because in right triangles, that in chapter 6, a bunch of diagrams like this. But check it out here. This is a little bit tough here because here, this is 9. That's unquestionably the smallest side in the blue triangle here. This is kind of like the larger leg in this triangle right here. So here we have smallest, here we have largest. The largest leg in this right triangle over here is the smallest leg in the red triangle right here. Okay, so these are hard diagrams. It's hard for people to see, and we'll continue working with this in chapter 6. So this is kind of like a bit of a preview. This side here, oops, I meant to switch to red to demonstrate that I'm talking about the other triangle here. This triangle length of 15, triangle's leg of 15 here, that's the smaller leg in this right triangle here. Okay, 25, what is it? That's the larger. So here, to see if triangle LNA is similar to triangle PNL, right? You'd have to have that kind of correspondence to it. So let's see, we go, because you want to do the corresponding side lengths, right? The largest in a triangle should correspond to the largest in another triangle, if they are in fact similar. So let's go ahead and set this one up here. Let's maybe do larger, I usually do smaller to larger. So let's do here, smallest is here, it's 9. And small, it goes to the 15 here. So 9 to 15, okay, that's our small ratio. Small side in LNA. NA would correspond to NL in this red triangle here. So that's 9 to 15. Does it equal, okay, this is our larger in this triangle here, and this is our larger in this triangle right here. Does it equal 15 to 25, okay? This is divisible by 3, right? 3, so this would be 3/5, okay, because 15 divided by 3 is 5, 9 divided by 3 is 3, and this here, 15, they're both divisible by 5, so this is 3/5 here. So our answer here for number 5 is yes. And why? Oh, I got ahead of ourselves here. Why is this yes? So here I just have 2 side lengths that are in proportion. Not all side lengths are in proportion necessarily. Well, what did I miss here? Ooh, the included angle, right? Check it out here. The included angle here is a right angle here. So this one here requires a bit of diving in deep to and kind of noticing. So perhaps you're just like a bit overwhelmed right now just by hearing this. I'd love you to meet with me. I'd love to talk to you about it. Come to office hours. I'm encouraging you guys to do that here. But yes, this, and then we have the included. So these side lengths here are in proportion, and they include a congruent angle, right? They include congruent angles here, right? So yes, by the SAS similarity theorem. Oh man, these puzzles, baby, puzzles, really interesting here. Okay, so let's check this one out here. This is the last one here, and this one I can tell is going to be no. I can tell it's going to be no. Why? Well, this 24 one is the largest in this triangle right here. Okay, but it's the smallest in this triangle, right? Right? This definitely trips people up here. Let's check this out here. So if I'm going to do this using my same logic, remember, stay organized here. Okay, I'm going to go smallest in this triangle. I'd have to go smallest in this triangle to smallest in this triangle to find a common ratio that maybe extends to the mediums and the largest corresponding sides here. So if I'm here 16, I'd go to the smallest in the second triangle here. So 16 is in that sort of zebra triangle right here. This is in that totally white triangle over here. 16 over 24. There's that ratio. Okay, then I'm going to go to my medium sides, okay, which is 20 to 30. Okay, so those are both in 2 to 3 ratios. Okay, so far so good. But now I'm going to go to my longest sides. In this zebra triangle here, 24 is my longest side. And that is going to go to 36. Oh, wait a second. Is this actually similar? This might actually be similar. Check this one out here. 16 over 24, well, they're both divisible by 8. That's going to be a 2 to 3 ratio. 20 over 30, okay, those are both divisible by 10. That's a 2 to 3 ratio. 24 over 36, they're both divisible by 12. Yes, 2 to 3 ratio. So here, all side lengths are in proportion. So yes, by SSS. Similarity. Drop the mic. Drop the mic. We got this one. We got it. Yes, we got it. Those are similar to one another. Incredible. Incredible. So thank you guys for watching. You got your exit ticket now. Man, there's a lot of stuff to take in here. Normally, just to give you again context, this won't be your problem set on Wednesday necessarily here. But normally what I do is like, hey, we lecture through, we talk about it, do some problems, and be like, hey, just go do these problems. Go have fun with them tonight. Don't worry about any exit ticket. Again, we're slowing things down this year, right? Because I know people fall behind here and there. Just want to keep that in focus, that you don't have to be perfect about this stuff right away. Usually it's just like, let's check it out, go have some practice with it. You don't have to be perfect right away. Okay? Email me if you have any questions. Thanks again for watching. Have a great rest
To the beat, y'all. Rock, rock. To the beat, y'all. And you don't stop. Rock, rock. To the beat, y'all. Rock, rock. To the beat, y'all. And you don't stop.